I like to think of capacitance as a bucket of charge. A capacitor is just a big bucket of charge. Capacitance is just a measure of how big that bucket is. So let's look at a few examples. If we had a nice wide, nice big bucket here, I'm going to pour some charge into it. Let's say I've filled it up with a certain amount of charge. I've got it filled up here. It's going to fill up to a certain height. That height is going to determine the potential energy. That's going to be equivalent to the voltage. Charge is just how much we poured into it, how much water. So the capacitance is just a measure of what's the capacity. A big capacitor would be like this. I pour in some charge, it goes up just a little bit. The voltage is going to be really small, so the voltage would be all that charge I've poured in divided by the capacitance. This big capacitor is going to go up just a little bit. On the other hand, if I had a small capacitor, I would think of that as a very tiny bucket or a long narrow tube. I pour in that same amount of charge, and now it's going to go up really high. Now with that same volume of water, if you think of it like that, pouring the charge in there, I'm going to have a much higher, a much greater voltage. Again, voltage is the charge divided by the capacitance. Now when we say that capacitance is equal to charge over voltage, that is measuring it. Remember, capacitance is a physical property of the conductors. It's just the area of the conductors, how far apart they are, maybe is there some other material between them. It's just a physical property. We can measure it by putting a certain amount of charge in and see what the voltage is, but that itself will not be the adding more charge is not going to change the capacitance. Changing the voltage will not change the capacitance. The capacitance is just a physical property of the device itself. Now, a few more things. You watch the Dan Fullerton videos to get some basic analysis on how to analyze series capacitors and parallel capacitors. Parallel capacitors, all you're doing is taking two buckets and putting them next to each other, so you're just adding the capacitors together. Very simple, very straightforward. Series is a little bit trickier. You wind up stealing charge from one to fill in the other, so I will refer you to the Dan Fullerton video for that. One more thing I do want to look at, though, is what if we have a mix of series and parallel capacitors? So let's say I've got some system here. I've got something here. I've got a capacitor here. I've got C1, and now I've got two other capacitors. I've got C2 and C3. And I want to know what is the equivalent capacitance of the whole thing. What we need to do, we need to break this into pieces. I'm going to do just a little bit at a time here. First thing I'm going to do, I'm going to look at this and say, oh, I've got C2 and C3. This is a parallel capacitor. So really, we can take this whole thing and replace it with, here's my C1 still there from before. Now I've got this guy. This is going to be C2 in parallel with 3. That's equal to C2 plus C3. Cool. Now I've got the series combination of these capacitors. On the other hand, I could have a setup, I could have something that looks like this. I might have a capacitor here. I've got a capacitor there. This whole thing in parallel with C3. I've got C1 here. Let's say here's C2, here's C3. I want to find the equivalent capacitance. Now I can replace this. This is equivalent to a single capacitor here. This is going to be C12. Here is C3. The C12 is going to be a little more complicated. It's a series capacitor, so we'd say 1 over C12 equals 1 over C1 plus 1 over C2. And finally, our equivalent capacitance is C12 plus C3. We'll go through a couple of simple examples of that today. So what I would suggest you do is watch the introduction to capacitance, watch the first Dan Fullerton video. It will tell you how to find capacitance for different geometries. Look at solving the series and parallel capacitance problems, and then we'll come back to dealing with these other cases. Oh, one more thing. So the notion of filling up the bucket and then pouring the bucket into something else, this will also work with problems if you've charged up a capacitance to a certain amount. So let's say I've got my bucket here and I filled it this high. So this says I've got a capacitor and it's at a certain voltage. And it's at a certain voltage. I have poured a certain amount of charge into this thing. We'll say this charge is going to be C1, V1. Now, I connected to a second capacitor. What we're doing here is I'm adding another bucket. I've got an empty bucket here. I'm going to fill that bucket with this charge. We're going to share the charge between the two. Now this may be a different size. This would be a different size capacitor. If I now take this charge and pour it into the other side, let's pick a different color here. I have to take charge from this one bucket, pour it into the other one. So I've got some here. I have to erase a little bit of the charge from this guy. We're going to get it down there. Total charge stays the same. So the total is going to be the same. So now we know that our total is going to be C1V final plus C2V final. If we've connected these together, let's say I've got some valve in here, I've connected these with a pipe, we know that they're going to be at the same voltage. So we know our final voltage is going to be the same for both capacitors. You think of the water is going to rise to the same level. The total charge is conserved, so the total charge in both capacitors together is going to be equal to the charge that we had at the beginning in just the one capacitor. And that's the way you solve those types of problems. All right, so good luck. I will catch up with you. There's the answer key is available to help guide you through this. I will be back with you on Tuesday and we'll pick it up from there. Thank you.